Assalamu alaikum students. Welcome to lecture number 3 of advanced nanomagnetism. So in this lecture we will discuss about the basics of nanomagnetism and we'll proceed further. The origin of magnetism, as we already did some work in early lectures, is due to the spin and orbital motion of electron, and the most dominant the spin motion of the electron. Nuclear spin motion is also present within the atom, but it is ignorable as the magnetic moment is inversely proportional to the mass, and the mass of the nucleus is very high. So that is why its nuclear magnetic moment is negligible. So the total magnetic moment of atom is the vector sum of the spin, orbital magnetic moments of electron, and nuclear magnetic moment. As I told you, the nuclear magnetic moment is very small due to this large mass of protons and neutrons in the nucleus. Therefore, it is neglected. Furthermore, the atoms with paired electrons have compensated opposite spins and compensated orbital motion. Therefore, the net magnetic moment of the atom is 0 for paired electrons. For the unpaired electrons atom, it has net magnetic moment due to these unpaired electrons, and it is represented in terms of the Bohr magneton. And here we can see the basics MH loops of the magnetic materials. You can see the diamagnetic material has a negative susceptibility, and it's a very weak effect present in all the materials with paired electrons, with atoms with paired electrons. Paramagnetic hysteresis loop is linearly behaving, while ferromagnetic has spontaneous magnetization. We already did some initial work in the previous lecture about, and then we have antiferromagnetic materials, and then we have also ferrimagnetic materials. So a nanoparticle is defined as a matter particle with size that lies between 1 to 100 nanometers in diameters, and it is composed of number of atoms, and the diameter lies between 1 to 100 nanometers. So the term nanoparticle is sometimes used for the particles with at least one dimension within the 100 nanometers. So here is the 3D image of platinum particles from the literature. We have taken, and their size is between 2 to 3 nanometers in diameter, showing rotating in liquid under electron microscope. Each particle has approximately 600 atoms. So we can also have multi-domain and single-domain nanoparticles. Usually particles with less than 100 nanometer, they are single domain, they have only one domain, and the particles above the 100 nanometer or above 200, they have more than one domain. And multi-domain means they have more than one domain. In the bulk ferromagnetic, ferro antiferromagnetic material, spontaneous magnetization is due to LS coupling, which results in the regions in which magnetic materials are aligned parallel and anti-parallel direction, known as the domains. The interface between two domains is called magnetic domain wall. So the magnetization rotation phenomena in multi-domain nanoparticles or multi-domain structure is due to domain wall motion. When you apply the magnetic field, the domains in the direction of the field grows, and those opposite are shrinks, so, and the domain walls are moving. While in the single domain, as we have no domain wall, so there the magnetic rotation is called the coherent rotation, and the coherent rotation is of the single domain, the huge core spin, coherently rotating in the direction of the applied magnetic field. So the single domain particles can be further classified into two into two regions, the blocked region and the unblocked region. If we decrease the size of the single domain particle to a certain limit, down to certain limit, their magnetic moment cannot, the huge single magnetic moment cannot stay or blocked in one direction due to thermal fluctuations. So this size limit gs of the magnetic nanoparticle in which it remains single domain depends upon the k effective of the material and exchange interaction of the integral of the material and ms situation magnetization of the material. So ds is the critical size limit for single domain nanoparticle, which is different for different materials. So magnetism in single domain nanoparticles is particularly different, very different from its counter bulk material. In single domain nanoparticle, the magnetism of individual particle is strong as compared to multi-domain particles. So we have different effects in single domain nanoparticles, which is due to the magnetic moment of individual atoms within the core, and also the aspect ratio. The surface has some surface defects which behaves differently as compared to the core of the nanoparticles, and interparticle interactions also plays important role. So all these factors make it different from this nanoparticles from their bulk. The surface effects are very dominant due to the lower coordination number, broken bonds on the surface, frustrated magnetic interaction due to the broken bonds. So there will be surface spin disorder, and also we have a reduced saturation magnetization in these materials, and also we will see some enhanced magnetization can be also available, possible in metallic or antiferromagnetic system. So the nanoparticle is particularly composed of the core, which behaves like a bulk material, and the surface has disorder surface spins, and the main difference between the nanoparticles and the bulk is their surface, which behaves differently under the applied magnetic field. And okay, there's some. So I have taken some material from these references, and I hope this short talk about the nanoparticles will be helpful for you. So particularly in the coming lectures, we will talk about the surface effects and how we can calculate the magnetic accessibility of these nanoparticles, small nanoparticles, and also how they behave when we increase the temperature or decrease the temperature. We will discuss about super paramagnetism in these nanoparticles, and there are a lot of interesting things will be available for you, and I hope that you people also will be motivated to read more from the literature, as due to the COVID-19 we have no other options other than online lectures. If you have any question, you can ask on the internet or email to me or on WhatsApp. We have a group there. So thank you.